everybody, welcome to our presentation. This is our midway presentation on the fish project that we're working on for the REU program. Just a little outline of the presentation that we're going to do today. We're going to go over a project background, a flow chart, and then the method that we use to get the outline for the specific fish, and also for the future work that we're going to do. The method that we use includes background subtraction, cleaning up the image a little bit, and then getting the outline out of that. For the background of the project, currently with new construction and with just the world changing and evolution changing, there's a lot of people who are looking into what types of fish we have, how many fish, populations in certain areas. So what a lot of the wildlife and fisheries and companies like that are doing is they're putting video cameras underwater, and then they have man hours go and look through all of the videos and then try and find different fish and classify them by species, count them, do things like that. So we're working on a program right now to implement a process of doing that, a computer model to do that, so there's not as many man hours. This is what we basically come up with for the part of the project that we're working on. First, we did a lot of research, which included getting familiar with the image processing toolbox in MATLAB, getting familiar with the fish species classification and previous methods of implementing that. Also, we met with people who were already assigned to the project to see what they're working on, what they need help with. The next thing we did was background subtraction, which we used an average of images. We included the mean in that, and then we cleaned up the image a little bit using thresholding, removing noise, object identification, and then after that we attempted to extract the outline. So far for background subtraction, we use two different methods of doing it. Well, we used one way of obtaining the background, which is averaging a sequence of pictures together. And then one method we used for subtracting it was just subtracting the background from one image. And then another method we used to subtract the background was subtracting an image from the background, but including the variance in that to try and get a better quality image. This is the first method that we used, which did not include variance. It was basically just averaging all the filters together. Once you averaged all the images together, you got the middle image right there, and that was your background image. And then once you subtracted the original from the background, that's the image you got over there. Okay. Philip's going to go ahead and talk about the second method.
All right. For my method of detecting the outline, first I obtained the background by averaging all the frames, and then I subtracted the image from the background. After that, I thresholded the image, and some of the fish weren't appearing, so I divided the original image by the variance, and I averaged that with the previous result and thresholded it again to get the new image. After that, I filtered out all the small objects and then heavily dilated the image and took the max and min of the x and y coordinates from each of the fish to isolate them. After I isolated each of the fish, I used a square method to fill the image, and then I detected the edges of the fish. So this is how I obtained the background. I just averaged all the frames together. There are some problems with this method, like if a fish stays too long in one place, it'll appear in the background. So in the future, we'll try and improve the background further by using stereo vision. This is just an image of the background that I got. So this is after I subtracted the background. On the left is the original image, and then on the right is the image subtracted from the background. Then I thresholded the image. Pixels with intensity less than 0.065 were changed to 0, and all other pixels are changed to 1. This method wasn't sufficient by itself, so I included the variance as well.
What's the range of the intensity in a typical image?
0 to 1.
Okay. 0.065 is like obtained empirically by like trial
Yeah,
and error?
yes. So this is the picture of the thresholded image. On the right side of the image, there's supposed to be a fish there, but you can't really see it, so that's why I included the variance. So then I divided the subtracted image by the variance, and this is the image divided by the variance, and as you can see on the right, the fish appears. So then I averaged the two results together, and this is what I got. So now I had the threshold again to remove the noise and separate it into white and black pixels. This is the image after thresholding. So then I had to filter out small objects because it had a lot of noise. Any object less than 250 pixels was removed from the picture, and this got rid of all the noise. This is the image after removing the small objects.
Going off of the original background subtraction method that just included the average only and did not take into account the variance, once you subtracted the image, you got basically just one fish. And then previously, this is what, if you use edge detection and then a dilated image and an eroded image, those are the outlines that you got, which was the goal of the project, was to get outlines, but these outlines were not sufficient. On the dilated image, you see it doesn't really, it has holes in it, and it's not really exactly the original image of the fish. And then the eroded image has a lot of holes in it, and the whole entire outline is broken. So in order to help that, I went back to the original image after you subtracted, and then I thresholded the image same way he did, using, it was a trial and error. We tried automatic thresholding, but it wasn't working. So with the trial and error, this is the image that you got after thresholding. And that was the first thresholding image, but there's actually another fish in here. You can't even see it in this image though. It's kind of up in the right-hand corner. So what I did was I took two thresholds. I took a positive and a negative threshold. And then this is what you get when you have that threshold. You can see the fish in the upper right-hand corner up there that was previously excluded. The only problem with this method was that right under the fish there's a shadow, so the negative threshold caught the shadow under the fish, which is what all the noise at the bottom is. And that's after all of the noise is removed also. And you can see the improvements in this. With a positive only threshold, this is the image that you got, but with the negative threshold, which you can see it fills in the eye and it fills in the fin, and then it also does capture the shadow, but it gives you the fish that's right here. And then once you do noise removal, you can see that there's kind of noise all over. So once you get rid of objects that are under a certain number of pixels, then you get rid of all the smaller noise, and it leaves you with just the fish. And then you can go ahead and identify objects. What that does is there is a feature in MATLAB that allows you to go through the image, and it looks for pixels that are grouped together, or pixels of one that are grouped together, and it identifies the different objects and shades them with different colors, so you can see how many objects you have. And then going from there, we're going to talk about erosion and dilation. We used a couple different methods for this to see what the best approach would be, and Philip's going to talk about the first method.
For my method, I used dilation in order to isolate the fish. So first I heavily dilated the image to fill in all the holes, and then after the image was dilated, a blurred outline of the fish could be seen. The fish has to be within the boundaries of the dilated image, so we can use the dilated image to isolate the fish. This is the image after dilation. So each fish was labeled using the BW label function in MATLAB. After that, we took the max and min of the x and y coordinates of each fish to isolate them. Then I used this information to form a box around the location of each fish, and After that, I used the infill command to fill in the small holes within the fish once it was isolated. So these are the pictures of all the fish once they've been isolated. So then I used the square method to fill in all the holes within the fish. This is the method. First, I place a square around pixels in question. For the examples I used a square of size 31 by 31, but in the future I'm going to make this dynamic based on the size of the fish. Then I divide the square into 4 quadrants, and if there's a significant amount of pixels, white pixels in each quadrant, I'm going to change the pixel in question to white. So these are results of after applying the square method with a square of size 31 by 31. You can see the outline is pretty well defined. So then the fish are completely filled in, and we can take the outline directly by using the edge command in MATLAB. And this is the pictures of all the outlines that I got. For the conclusions of the square method, the benefit of the square method is that no dilation of the image is required to detect the edges. Therefore, the edge will most likely be more accurate than with dilation methods. The current method detects the outline fairly well, but can clearly be improved further.
Another approach to finding the outline of the fish images not using the square method also includes dilation and erosion. For the first image, this is a dilated image, and then this is the eroded image. Erosion just kind of eats away at the outer edge, and dilation fills in the outer edge of the whatever object is in the image. If you use outline detection based on the eroded image, if you take the image and you subtract the original image minus the eroded image, you can get outlines. You see this outline is kind of broken up, but the one over there is pretty well defined. It has a thicker border. And then there's another method where if you take the dilated image and you subtract the normal image, you also get 2 pretty well defined outlines. The first one's a little bit lighter, the second one's a little bit thicker. You can set the border to different sizes if you choose. This is a good outline because it gives you all the features in the inside. You can see the fin, and you can see the eye for future classification if you ever need to use those features. Problems that we've encountered in this project so far include thresholding. As I mentioned earlier, the automatic thresholding doesn't work for every image. It works for some images, not other images, so as of now, there's really no way of telling what image is going to work for, so it's easier to go in and look for the threshold. And also, with including the negative threshold, it's also keeping the shadow under the fish. Another problem is that the techniques are not transferable in different sequences. So what that means is that one of our techniques that may work on a camera in one location is not transferable to a camera in another location. So there's ways to make it more universal. We just have to work on that. And then some of the outlines you get are pretty rough. And then for the future, we're thinking of doing a couple things. One thing that was brought to our attention and that we're considering doing is creating a new background using 3 different criteria. One criteria would be stereo vision. A lot of the images that we do have in the database have a left and a right image, so you can use that to kind of create a semi-3D image and subtract what's in the background and what's in the foreground, because what's in the foreground should be the fish. And if you also include optical flow and then the averaging of all of the images together, all that together can create a better background, which, since the background is the base of the project, it'll help in the future classification if you have a really good base fish. And then we'll also take into, this is for the square method, we'll take into account like other aspects, such as like the distance between the pixels and the closeness in the pixels. And then we'll use that to determine whether to fill in the pixels or not when trying to recreate the image of the fish from the subtracted background, because sometimes it's broken up. These are just some of the sources we used. So we thank y'all for listening today. Does anybody have any questions? Yes?
So currently, do you have any concrete measure on how well you can segment the fish or for later for classification or other purposes?
What do you mean segment the fish?
Well, like, can you go back to the slide on the current status of the future work?
Okay, the future work.
And we also say you want to improve on the background subtraction and also maybe highlight the outline of the fish. Do you have any measure on how good you expect your method to perform?
There's really no. I mean, we have what they've previously completed in the. They've done project. This is a part of an overall project. So what they have done before, they have extracted outlines before, and they have subtracted backgrounds before. So we're kind of using that as a measure and trying to improve that. If that's the cap that we can get to, then we really haven't improved anything. And if we're not making it there, then we haven't gotten to what is already completed. So what's previously been done is kind of the measure that we're using as of now.
You say optical flow. Did any previous work use any optical flow method?
Yeah, there was one method that was shown me by one of the grad students where optical flow was used. It was used by itself, and there was another one where averaging was used and averaging was used by themselves. There's a lot of other methods they've currently used, like there's a graph cut method, and there's other methods that they use to subtract the background, but they're all kind of giving the same background area. There's not really there's not a very well-defined background. There's a background that's good enough to use for now, but we're thinking that if we can get a better background, that'll give us a better base fish for the classification section to go ahead and use in order to classify that fish.
How many different image sequences do you have in order to compare different methods?
In the database, there's at least a dozen different images sequences, and then each sequence has about at least between 150 to 250 photos in it. Those do include left and right. So the ones that we were working on, I think, has 75 or so images of like 75 left and right similar images. And there's about at least like a dozen of different sequences that we can use to tell.
That's probably enough for comparing different methods.
Yes. Was that any other questions?
No.
Okay. All right. Thank y'all.
Thanks. We're not going to clap because we know how many we have.